There is an experiment that has been repeated in laboratories around the world, verified by multiple independent teams, and confirmed with increasing precision over decades. Its results are not disputed. And yet what it implies about the nature of time, history, and reality itself remains one of the most unsettling conclusions in the entire history of science. The experiment involves light. It involves a choice you make today. And it reveals that your choice today can be correlated with the path a particle took billions of years ago, before our solar system existed, before the Earth formed, before any life ever looked up at the sky and wondered what was out there. This is not metaphor. This is not philosophy. This is a measurable, reproducible physical phenomenon. It is called the delayed choice quantum eraser. And understanding it requires us to dismantle almost every intuition we have about cause, effect, and the direction of time. Let us start from the ground floor, not with speculation, but with one of the most well-established experimental facts in physics. In the early 20th century, scientists began probing the behavior of light at the smallest possible scales. They discovered something immediately contradictory. Light behaved differently depending on how you looked at it. Under certain conditions, it spread out across space like a wave on the surface of water, creating ripples and interference patterns. Under other conditions, it behaved like a tiny discrete bullet striking a detector at one specific point, the same substance. Two entirely different behaviors. And the behavior it chose depended inexplicably on what kind of measurement you performed. This dual nature was formalized into one of the strangest demonstrations in experimental science, the double-slit experiment. Imagine a light source that fires individual photons, one at a time. Not a beam of light, but a single particle of light, fired alone, like a bullet from a gun. In front of this source is a barrier with two narrow vertical slits cut into it. Behind the barrier is a screen that records where each photon lands. If you fire thousands of photons one at a time without observing which slit they pass through, something deeply strange happens on the back screen. You do not see two simple columns of dots behind the two slits, which is what you would expect if photons were simply tiny balls. Instead, you see a pattern of alternating bright and dark stripes spread across the entire screen, dozens of stripes. This is called an interference pattern, and it is the unmistakable signature of wave behavior. This pattern arises because each photon, traveling alone, somehow passes through both slits simultaneously. More precisely, the photon is described by a quantum wave function, a mathematical object that encodes all the possible states the particle could be in. This wave function splits at the barrier and passes through both slits at the same time. The two resulting waves then collide with each other on the other side. Where the peaks of the two waves line up, they reinforce each other, creating a bright stripe. Where a peak meets a trough, they cancel each other out, creating a dark stripe. This is wave interference. It is the same phenomenon responsible for the colorful patterns you see on soap bubbles or oil slicks. The only difference is that in those cases, light waves from a continuous source are interfering. In the double-slit experiment, a single particle is interfering with itself. That sentence is worth pausing on. A single particle interfering with itself. It passed through both slits at the same time, despite being a single indivisible object. This is not a conceptual trick or a mathematical convenience. It is a physical reality that has been demonstrated countless times with photons, electrons, atoms, and even large molecules containing hundreds of atoms. Now introduce a detector. Place a small measuring device next to the slits to determine which slit each photon passes through. You fire a photon. The detector registers. Left slit. You look at the back screen. The interference pattern is gone. Instead of alternating stripes, you see two simple clumps of dots, one behind each slit. Clean, ordinary, particle-like behavior. The photon picked one slit, traveled through it in a straight line, and hit the screen directly behind it. This result is just as consistent no matter what kind of detector you use, no matter how gentle or non-invasive the measurement. As long as the measurement makes which path information available in principle, as long as the information exists anywhere in the universe, the interference pattern disappears. The photon acts like a particle. Remove the detector, and the interference pattern returns. Add it back, and the stripes disappear again. This is the observer effect. It does not require a conscious mind. It does not require a scientist actively paying attention. What matters is whether the information about which path the photon took is encoded somewhere, in any physical system, in any way that could in principle be read. The moment such information exists, the photon loses its wave-like character and behaves as a particle. For several decades, physicists accepted this phenomenon while assuming something about its timing. They assumed the collapse happened at the moment of measurement. When the photon reached the slits and the detector registered its path, the wave function collapsed at that instant. The photon made its choice then and there, and everything downstream from that moment unfolded accordingly. Cause, then effect. A sensible, linear timeline. In 1978, a physicist named John Wheeler proposed an experiment that completely dismantled this assumption. Wheeler was one of the most creative and rigorous physicists of the 20th century. He worked alongside some of the founding figures of quantum mechanics and made fundamental contributions to our understanding of black holes and space-time. His approach to thought experiments was legendary. He had a gift for designing hypothetical scenarios that exposed the deepest contradictions in physical theory. His proposed experiment was simple in concept but terrifying in implication. He asked, "What if we do not decide how to measure the photon until after it has already passed through the slits? What if the photon has already traveled through the barrier and is already in flight on its way to the screen, and only then do we choose whether or not to look at which path it took?" In a laboratory setting, the timescales involved are so small that this question might seem academic. Photons travel at the speed of light, roughly 300 million meters per second. The distance from slits to screen in a lab might be a meter or two. The photon covers that distance in a few billionths of a second. Even if you could set up a last-minute detector switch, the timing would require extraordinary precision. So Wheeler imagined scaling the experiment up to cosmic proportions. He proposed using the universe itself as the experimental apparatus. Here is how his cosmic thought experiment worked. Somewhere in the distant universe, far beyond our galaxy, there exists a type of object called a quasar. A quasar is an extraordinarily luminous celestial object, the active nucleus of a galaxy, powered by a supermassive black hole consuming enormous amounts of material. Quasars can outshine entire galaxies of hundreds of billions of stars, and some of them are so distant that their light has been traveling toward us for over 10 billion years. Now imagine that between this quasar and Earth, sitting roughly halfway along the light's journey, there is a massive galaxy. This galaxy contains hundreds of billions of stars and is so massive that its gravity warps the fabric of space-time around it. When light from the distant quasar reaches this intervening galaxy, it is forced to bend around it, following the curves of warped space-time. The light can go around the left side of the galaxy, or it can go around the right side. Both paths lead to Earth. Both arrive at roughly the same time after journeys measured in billions of years. From our position on Earth, we would see two images of the same quasar appearing at slightly different positions in the sky because the light arrived from two slightly different directions after bending around opposite sides of the galaxy. This is called gravitational lensing, and it is not a theoretical construct. We observe it routinely with modern telescopes. Some quasars have been observed with 4 or even more distinct images formed by gravitational lensing around intervening objects. Wheeler saw in this natural phenomenon an enormous version of the double-slit experiment. The quasar is the light source. The intervening galaxy is the barrier. The two paths around the galaxy are the two slits. And the entire journey, billions of light years of travel through the void of space, is the space between the slits and the back wall. Now here is the key. An astronomer on Earth tonight, standing at a telescope, observing this gravitationally lensed quasar, has a choice. There are two fundamentally different ways to measure the incoming light. The first option is to measure which path the photon took. The astronomer can orient the telescope to detect photons coming specifically from the left image or the right image. This measurement extracts which path information. If the telescope detects a photon arriving from the direction of the left image, it means that photon traveled around the left side of the galaxy. The path is known. According to the logic of the double-slit experiment, This means the photon was a particle the entire time. It picked one route and traveled it. The second option is to measure interference. Instead of resolving the two images separately, the astronomer can use an instrument called an interferometer, which combines the light arriving from both directions into a single detector. If the photon traveled as a wave, if its wave function propagated around both sides of the galaxy simultaneously, then the two wavefronts arriving from different directions will interfere with each other inside the photon instrument, producing a measurable interference pattern. According to everything the double-slit experiment taught us, which measurement you perform determines which behavior you get. Look for a particle and you see a particle. Look for a wave and you see a wave. But here is where Wheeler's thought experiment becomes philosophically catastrophic. The photon left that quasar billions of years ago. It reached the intervening galaxy billions of years ago. At that moment, by the standard logic, it should have already made its choice. It was either a particle, choosing one path around the galaxy, or a wave, spreading around both sides simultaneously. That decision, if it happened at the barrier, happened billions of years before the Earth existed. Yet the astronomer tonight, making a measurement choice on Earth in the present moment, determines which behavior is observed. If the astronomer chooses to measure the path, the results are consistent only with the photon having traveled one side as a particle. If the astronomer chooses to measure interference, the results are consistent only with the photon having traveled both sides as a wave. The choice made in the present moment appears to determine which of these two incompatible histories the photon had. A history that was supposedly already written billions of years ago, long before anyone existed to make any choice at all. Wheeler summarized this with characteristic precision. He said that no phenomenon is a real phenomenon until it is an observed phenomenon. The universe does not commit to a particular history until someone or something interacts with it in the present. The past, in this framework, is not a fixed record. It is a superposition of possibilities that collapses only when measured. For 20 years after Wheeler proposed this cosmic thought experiment, it remained exactly that, a thought experiment. No one had the technology to actually test the delayed choice scenario in a controlled laboratory setting with sufficient precision to rule out alternative explanations. That changed in 1999. A team of researchers led by Yoon-Ho Kim at the University of Maryland constructed a brilliantly clever experimental apparatus that finally made the delayed choice quantum eraser testable with photons in a laboratory. Their setup required several components. A laser provided the initial light source. A special type of crystal called a beta-barium borate crystal served as the heart of the apparatus. When a laser photon enters this crystal, the crystal can convert it into two lower energy photons through a process called spontaneous parametric down conversion. These two new photons are created simultaneously from the energy of the original photon, and they are quantum mechanically entangled with each other from the moment of their creation. Quantum entanglement means that these two photons share a joint quantum state. Their individual properties are not independently defined. Instead, certain properties of one photon are linked to corresponding properties of the other, regardless of the distance between them. Measuring a property of one photon instantaneously affects the probability distribution for measuring the corresponding property of the other, no matter how far apart they have traveled. In Kim's experiment, the entangled pair produced by the crystal is called a signal photon and an idler photon. The two photons immediately travel in different directions when they are created. The signal photon heads toward one detector. The idler photon heads toward a more complex arrangement of optical components designed to measure its path or erase that path information. The signal photon travels a short distance and hits a detector called D0. This detector records where the photon landed. It marks a single dot on a screen. The signal photon's journey is over the instant it hits D0. The idler photon, meanwhile, travels a longer and more complicated path. It passes through a series of beam splitters. A beam splitter is an optical device that gives a photon a 50% chance of reflecting and a 50% chance of passing straight through. The idler photon encounters several beam splitters in sequence, and the arrangement of these beam splitters determines the outcome. In some configurations of the apparatus, the idler photon encounters a beam splitter that routes it to one of two detectors based on which path it took. If the idler photon came from the left slit, it goes to detector D3. If it came from the right slit, it goes to detector D4. In this configuration, the witch path information for the idler photon is preserved. You can know which slit its twin signal photon went through by checking where the idler ended up. Because the photons are entangled, knowing the path of one tells you the path of the other. In other configurations, the idler photon's path information is erased. The beam splitters are arranged so that photons from the left path and photons from the right path are both routed to either detector done or detector D2, with no way to tell which path any individual photon took. The left path information and the right path information are mixed together. The witch path information is gone, erased. Now here is the critical timing. The idler photon's path is longer than the signal photon's path. This is intentional and essential. The signal photon hits detector D0 and records its position before the idler photon has finished its journey. The signal photon story ends before the idler photon reaches the beam splitters that will determine whether its path information is preserved or erased. So you have this sequence. The signal photon hits the screen. Its landing spot is recorded. Its journey is complete. Only after this does the idler photon pass through the apparatus and arrive at one of the 4 detectors, where the path information is either read out or destroyed. Now you sort the data. You take all the landing spots of the signal photons and ask, among the signal photons whose idler twins ended up at D3, what is the pattern of their landing spots? What about those whose twins ended up at D4? What about done and D2? The results are startling. Signal photons whose idler twins ended up at D3 or D4, the detectors that preserve witch path information, show no interference pattern. Their landing spots form 2 broad clumps, like ordinary particles that went through one slit or the other. Particle behavior. Signal photons whose idler twins ended up at done or D2, the detectors that erase witch path information, show clear interference patterns. When you plot their landing positions, alternating bands of high and low hit density emerge precisely. Wave behavior. The signal photon, which already hit the screen before the idler photon made its choice, somehow knew in advance what was going to happen to its twin. Or rather, the correlation between past and future is so complete that the signal photon's landing position is precisely predictive of what will happen to the idler nanoseconds later. If the idler's path was going to be preserved, the signal landed as though it were a particle. If the idler's path was going to be erased, the signal landed as though it were a wave. The signal photon's behavior retroactively matches the future measurement of the idler. From a purely causal perspective, the sequence appears inverted. The effect the signal photon's wave or particle behavior appears to precede the cause the decision to erase or preserve the idler's path information. The record of the past was not written until the future event occurred. The immediate instinct when confronted with this result is to ask the most practical possible question. Can we use this to communicate backwards in time? If my choice today correlates with a photon's behavior yesterday, could I use that correlation to send a message to my past self? Could I encode information, perhaps something as simple as yes or no, into the future choice and have it appear in the past behavior of the signal photons? The answer is no. And the reason why is itself deeply illuminating about the nature of quantum reality. Here is why you cannot send information backward in time using this experiment. Suppose you are standing at the screen, watching the signal photon land in real time. You want to see, right now, whether the signal photons are forming an interference pattern or a clump, so that you can decode a message being sent to you from the future. Look at the screen. What do you see? You see a blur. A smooth, featureless distribution of hits that reveals no pattern whatsoever. It looks like random noise. No stripes, no clumps, just a fuzzy blob of light. This happens because all 4 subsets of data, the wave pattern from done, the wave pattern from D2, the particle clump from D3, and the particle clump from D4 are all landing on the screen simultaneously, mixed together. The wave patterns from done and D2 are actually shifted relative to each other in a very specific way. Where one has a bright stripe, the other has a dark stripe. When you add them together, the stripes cancel out perfectly, producing a featureless distribution. Similarly, the particle clumps and the wave patterns, when combined, produce nothing readable. Every pattern is hiding inside the total distribution. The screen, viewed in real time without sorting the data, is completely uninformative. No message can be extracted from it. The only way to see the hidden patterns is to already know the future data. You have to wait for the idler photons to finish their journey, get detected at done, D2, D3, or D4, and have that information transmitted to you through a normal classical channel, a wire, a radio signal, a phone call which cannot exceed the speed of light. Only once you have that future information can you go back and sort the past data on the screen and reveal the patterns hidden within it. This means you can only discover the correlation after it has fully occurred. You can never use it to gain advanced knowledge. You cannot see the future event before it happens. You can only look backward afterward and recognize that the two events were linked. This constraint is known as the no communication theorem, or the no signaling theorem. It is a fundamental mathematical result in quantum mechanics that proves quantum correlations across time or space cannot be used to transmit information. The correlations exist, they are real, but they are, in a precise technical sense, inaccessible in any way that could be leveraged for communication. Nature has engineered a system that is simultaneously as strange as possible and as non-exploitable as possible. The weirdness is real, the loophole is closed. This brings us to a deeper question, one that physicists and philosophers have been wrestling with since these results were first confirmed. What do these experiments actually tell us about the nature of reality? The most straightforward interpretation is also the most disturbing one. Quantum mechanics describes a universe in which the past is not fully real until it is observed from the present. Consider what it means for a particle to have a history. We intuitively assume that every object that has ever existed has left a definite trail through time. The photon that left that distant quasar billions of years ago either went around the left side of the galaxy or it went around the right side. One of those things happened. The history exists, whether or not anyone was there to see it. The quantum eraser experiment challenges this at the deepest level. According to the formalism of quantum mechanics, the photon did not travel one path or both paths in any definite sense until a measurement was made. Before measurement, the photon is described only by its wave function, a mathematical representation of all the possible paths it could have taken, weighted by probability. This is not a statement about our ignorance of the true path. It is a statement about the actual physical state of the system. The wave function is not a summary of what we don't know. It is a complete description of what exists. When we make a measurement, the wave function collapses to one specific outcome. A path is selected, a history is defined, but crucially, this collapse is not constrained to affect only the present and future. Because the photon's history was never defined prior to measurement, the collapse also defines what the past was. The act of measuring now determines what happened then. This is a radical departure from classical thinking. In classical physics, the past is always fixed. Measurements reveal pre-existing facts. A rock that fell off a cliff followed a specific parabolic trajectory, and the fact of that trajectory existed whether or not anyone measured it. The rock did not need an observer to have had a definite path. Quantum mechanics denies this for quantum objects. The photon has no definite path until a measurement commits it to one. And because the commitment happens at measurement, and measurement can happen long after the events in question, the commitment to a specific past can happen long after the events in question. Niels Bohr, one of the founders of quantum mechanics, argued for precisely this position throughout his career. He insisted that quantum mechanics does not describe an objective reality existing independently of measurement. It describes the results of experiments. The properties of a quantum system are not things the system has. They are things the system yields when asked the right question. Albert Einstein spent decades arguing against this view. He found it philosophically intolerable that the universe should require observers to assign definite properties to physical objects. He asked, famously, whether the moon exists only when we look at it. He believed that any complete physical theory must describe an objective reality that exists independent of our observations. He called any theory that failed to do this incomplete. The Bell test experiments, first proposed by physicist John Bell in 1964 and confirmed experimentally beginning in the 1980s, showed that Einstein's intuition was wrong. Any hidden variable theory, any attempt to explain quantum behavior by invoking pre-existing definite properties that we simply haven't measured yet, either violates the predictions of quantum mechanics or requires instantaneous correlations across arbitrary distances. Since quantum mechanics has been confirmed with extraordinary precision, And since experiments have rigorously ruled out local hidden variable explanations, we are left with a universe that is fundamentally non-classical. The delayed choice quantum eraser takes this conclusion one step further. It is not just that the properties of quantum objects are undefined before measurement. It is that the definition of what happened in the past depends on what measurements are made in the present. The history of a particle is not written until someone or something observes it and writes it down. This has strange implications for how we think about the arrow of time. We experience time as moving in one direction. The past is fixed and settled. The future is open and undetermined. We call this the asymmetry of time. It is baked into our experience of consciousness, our experience of memory, our understanding of causality. We remember the past and anticipate the future, never the reverse. The quantum eraser suggests this asymmetry may be more provisional than we thought, at least at the quantum level. While the no-signaling theorem ensures that macroscopic causality is preserved, the quantum correlations underlying our macroscopic world appear to be genuinely time-symmetric. The equations of quantum mechanics, like the equations of classical mechanics, are symmetric under time reversal. They work equally well going forward and going backward. The arrow of time we experience is an emergent property, possibly related to thermodynamics and the increase of entropy, not a fundamental feature of the quantum world. Recent decades have seen physicists push even further into the implications of these ideas. A framework called retrocausal quantum mechanics has been developed by researchers including Yakir Aharonov and John Kramer. In this interpretation, quantum systems send information both forward and backward in time. A measurement in the present sends a signal backward in time to the particle at the moment of its creation, and the particle sends a signal forward to the measurement. The behavior we observe at the measurement is the result of these two signals negotiating with each other across time. Cause and effect become a mutual agreement rather than a one-way arrow. This interpretation has not achieved mainstream acceptance, but it has the advantage of making the delayed choice results feel intuitive rather than paradoxical. If information can travel both ways in time at the quantum level, then the correlation between the present measurement and the past behavior of the particle is exactly what you would expect. The two events are exchanging information across time, producing a consistent shared history. Another influential framework is the many worlds interpretation, developed by Hugh Everett in 1957. In this interpretation, quantum measurement does not collapse the wave function. Instead, all possible outcomes occur simultaneously, each in its own branch of a vastly expanded universe. When you measure a photon and find it went through the left slit, you have not forced the universe to select that outcome. Instead, the universe has split. In one branch, you measured left. In another branch, you measured right. Both branches are equally real. The delayed choice results in the many worlds framework are explained without any retrocausality. The branching of the universe happens at measurement, not before. The history of the photon is different in different branches, but no branch retroactively alters another. The apparent backward influence is an artifact of our experience of time within a single branch. The challenge for the many worlds interpretation is that it offers no way to empirically distinguish itself from other interpretations, and it requires accepting the existence of an incomprehensibly vast and constantly multiplying number of parallel universes, none of which can interact with our branch in any directly detectable way. A third framework, relational quantum mechanics, developed by Carlo Rovelli in the 1990s, takes a different approach entirely. In this view, quantum states are not properties of objects. They are properties of relationships between objects. The photon does not have a definite path in absolute terms. It has a definite path relative to a specific observer who made a specific measurement. A different observer who made a different measurement would have a different relationship with the same photon, and both relationships are equally valid. Time, in this framework, is also relational. The past is not an absolute fixed structure. It is a set of correlations between physical systems. The question of what happened before only has meaning relative to a particular set of subsequent measurements. There is no single universal history of the universe that all observers agree on. History is an observer-dependent construct. All of these interpretations agree on the experimental predictions. They all predict the same results for the quantum eraser experiment. the Bell tests, the double-slit experiment, and every other quantum mechanical test we have devised. They disagree on what those results mean for the nature of reality. The question of which interpretation is correct is, at present, unanswerable experimentally. It may be a question that can never be answered by experiment alone, because the interpretations are designed to agree on all observational consequences. What we can say with confidence is what we observe. Quantum systems exhibit correlations that cannot be explained by any theory that assumes classical, local, objective properties. The history of a quantum system is not determined until it is measured. Measurements made in the present are correlated with events in the past in ways that respect the no-communication theorem but defy ordinary causal intuition. The experiments are real. The results are confirmed. The implications are genuinely radical. In the years since Kim's 1999 experiment, researchers have continued to push the boundaries of delayed choice experiments. In 2007, physicists at the University of Vienna performed a delayed choice experiment with single photons, in which the decision of whether to observe wave or particle behavior was made by a quantum random number generator, ensuring that the contrassense choice was as random and last-minute as physically possible. The results matched quantum mechanical predictions precisely, with no deviation. In 2012, a team from the Australian National University performed a Wheeler delayed choice experiment using helium atoms rather than photons, demonstrating that the effect is not specific to light but applies to massive particles as well. Matter, not just light, exhibits this strange dependence of past behavior on present measurement. In 2017, physicists implemented a delayed choice entanglement swapping experiment, in which entanglement between two photons was created after both photons had already been measured and had ceased to exist as coherent systems. The correlations persisted even under these extreme conditions. Each experiment presses the paradox harder and finds the same result. The universe maintains its quantum character under increasingly extreme conditions of delayed choice, expanding scales, and more sophisticated attempts to catch it in a classically definite act. There is a thread in all of this that connects back to some very old questions in physics, questions that go beyond quantum mechanics to the structure of time itself. We experience time as having three distinct regions: the fixed past, the present moment, and the open future. This asymmetric structure is so fundamental to our experience that it is difficult to imagine reality being any other way. Yet the fundamental equations of physics, both classical and quantum, do not encode this asymmetry. The laws of gravity, electromagnetism, the strong and weak nuclear forces, and quantum mechanics are all time-symmetric. They work exactly as well running forward as running backward. If you filmed a collision between two particles and played the film backward, both versions of the collision would be valid solutions to the equations of physics. The asymmetry of time, we experience the sense that the past is closed and the future is open, that causes precede effects, that memory flows in one direction, appears to emerge from something outside the fundamental laws of physics. The leading candidate is the second law of thermodynamics, the principle that entropy, the measure of disorder in a physical system, tends to increase over time. But entropy is a statistical concept, not a fundamental law. It tells us that because there are vastly more ways for a system to be disordered than ordered, highly ordered systems tend to become more disordered over time, simply because disordered states are overwhelmingly more likely. This statistical tendency produces the arrow of time we experience, but it does not write it into the fundamental equations. The delayed choice quantum eraser sits at the intersection of these deep puzzles. It shows us that quantum correlations across time are possible. It shows us that the definition of what happened in the past depends on what measurements are made in the present. And it shows us that all of this is compatible with macroscopic causality. The ordinary cause and effect relationships we experience in everyday life are protected, even as the quantum world operates with a startling indifference to the direction of time. What remains unknown is profound. We do not know why the macroscopic world behaves classically when the quantum world does not. We do not know at precisely what scale, or through precisely what mechanism, the indefiniteness of the quantum world transforms into the apparent definiteness of the classical world. This is the measurement problem, and it is among the deepest unsolved questions in physics. We do not know which interpretation of quantum mechanics, if any of the current ones, is correct. We do not know whether quantum indeterminacy is a fundamental feature of reality or a sign that our current description of physics is incomplete. We do not know whether time is fundamental or emergent. Several approaches to quantum gravity, the attempt to reconcile quantum mechanics with general relativity, suggest that time may not be a fundamental feature of the universe at all. It may be something that arises from more fundamental quantum correlations between physical systems, real only in the approximate macroscopic world of our everyday experience. And we do not fully understand the nature of the now, the present moment from which all measurements are made, from which all choices about how to observe are executed, and in relation to which the past and future of quantum systems are defined. In relativity, there is no universal present moment. Different observers moving relative to each other disagree about which events are simultaneous. The present is relative. Combined with quantum mechanics, this produces a picture of reality in which the past is not fixed, the future is not open in any simple sense, and the present is not universal. What we are left with is a universe that resists, at its most fundamental level, the intuitive picture of reality we navigate through every day. The world of our experience, solid, continuous, causal, with a definite past and an open future, is a construction. It is built from something more fundamental, something that does not have these features in any obvious way. The delayed choice quantum eraser is one of the clearest windows we have into that deeper level. It is an experiment you can do in a laboratory. Its results are unambiguous. And what it tells us about the nature of time, history, and observation is stranger and more interesting than almost any other result in science. The past is not a fixed record preserved in some metaphysical archive. It is a set of correlations between physical systems that resolve into definite form only when measurements are made. The universe does not have a definite history stretching back to the beginning of time, waiting to be discovered. It has a history that is continuously being written by the interactions happening in the present. We are not passive observers watching a universe that would unfold the same way whether we existed or not. We are participants in a process of continuous becoming. Our measurements, our observations, our choices about what to look at and how to look at it, these do not just reveal the world, they participate in constructing it. The photon that left a distant quasar billions of years before the Earth existed did not have a definite history until someone on Earth, tonight, pointed a telescope at it and asked a question. That question reached back across billions of years of travel time and defined what the photon had been doing all along. And the universe, in its full quantum strangeness, answered. If you found this exploration of time and quantum reality as mind-bending as it deserves to be, consider sharing it with someone who thinks they understand how the universe works. And if you want to keep going deeper into the science of the genuinely strange, the experiments that hold up under scrutiny and still break your intuition, make sure you stay with us. The next discovery is always stranger than the last. What physicists are working on now only deepens the mystery. Teams around the world are extending delayed choice experiments to even greater distances, using satellites to separate the entangled particles by thousands of kilometers before measurement. Others are exploring whether the correlations persist when the time between the signal photon's detection and the idler photon's measurement is extended not by nanoseconds, but by milliseconds, seconds, or longer. Still others are probing whether macroscopic objects, not just photons or atoms, but things we can almost see with the naked eye, can exhibit delayed choice behavior if isolated sufficiently from their environment. Each of these experiments is a probe into the question of where quantum mechanics ends and classical physics begins, of where indefiniteness becomes definiteness, of where the smeared, probabilistic, time-indifferent quantum world transitions into the sharp, causal, time-directed world we live in. We do not yet know where that boundary is. We do not yet know if it is sharp or gradual. We do not yet know whether it is a real physical boundary or an artifact of how we describe systems that are too large for us to track in full quantum detail. What we do know is that the universe, at its most fundamental level, accessible to experiment, does not work the way we thought. The results are in. They have been replicated. They have survived every attempt to explain them away with more conventional physics. The universe is stranger than it looks. and the experiments designed to test how strange it is keep confirming. Stranger still. To truly appreciate how revolutionary the delayed choice quantum eraser is, it helps to understand just how recently we developed the conceptual tools to even ask these questions. For most of human history, our best thinkers assumed that time flowed in a single direction, from a fixed, settled past toward an open and undetermined future. This was not a casual assumption. It was built into every branch of science, every philosophical framework, and every human institution, from memory to law to accountability. The idea that the past could be genuinely undetermined, not just unknown, but actually undefined until observed, would have been considered not just wrong but incoherent for nearly all of intellectual history. You cannot have courts of law if the past is indefinite. You cannot have memory if what you remember was never actually definite when it happened. You cannot have science itself, which depends on the assumption that experiments produce definite records of definite events, if the events were not definite until the records were made. Yet this is precisely what quantum mechanics appears to say, and the laboratory experiments confirm it. The history of how we arrived at this conclusion is one of the great intellectual journeys in human thought. It began not with philosophical speculation, but with a simple and puzzling observation about light. In the 19th century, physicists had definitively established that light was a wave. The experiments of Thomas Young in 1801 had shown double-slit interference patterns for light. James Clerk Maxwell's equations in the 1860s had described light as an electromagnetic wave, predicting its speed from the fundamental constants of electricity and magnetism. Light was a wave. This was established, confirmed, and considered closed. Then Max Planck, in 1900, trying to explain the spectrum of radiation emitted by hot objects, found that he could only produce a correct mathematical description by assuming that light energy came in discrete chunks quanta rather than in continuous waves. The energy of each quantum was proportional to the frequency of the light, with a proportionality constant that now bears his name, Planck's constant. Planck did not believe this was a real physical claim. He thought it was a mathematical trick that happened to produce the right answer. He was famously uncomfortable with the implications of his own discovery. Albert Einstein, in 1905, took Planck's idea seriously and used it to explain the photoelectric effect, the phenomenon in which light shining on a metal surface causes electrons to be ejected. The details of the photoelectric effect only made sense if light actually consisted of discrete packets of energy, not continuous waves. Einstein called these packets light quanta, and they would later be named photons. Einstein received the Nobel Prize for this work in 1921. But even as he was awarded for demonstrating the particle nature of light, he was becoming deeply uncomfortable with the broader implications of quantum theory. The emerging quantum mechanics of the 1920s, developed by Heisenberg, Schrödinger, Bohr, Born, and others, seemed to Einstein to be incomplete. It described results of measurements without giving an account of what physical reality was doing between measurements. Einstein wanted a deeper theory, one that was deterministic, objective, and complete. He spent the rest of his life searching for it and never found it. The double-slit experiment, in its various forms, was one of the key battlegrounds for these debates. The experiment had been performed with electrons beginning in the 1920s and 30s, confirming that massive particles, not just photons, exhibited wave interference when unobserved and particle behavior when observed. The quantum mechanical explanation was clear. Unobserved particles are described by wave functions that spread through space and interfere with themselves. Observation forces the wave function to collapse to a definite state, ending the interference. What remained deeply controversial was the interpretation. What is the wave function? Is it a real physical wave propagating through space? Is it a mathematical tool for calculating probabilities with no independent physical reality? Is the collapse of the wave function a real physical process? And if so, what triggers it? Does it require consciousness, or does any physical interaction suffice? These questions, grouped under the label the measurement problem, remain unresolved today. Different physicists answer them in different ways, and the different answers constitute the different interpretations of quantum mechanics. In the Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the late 1920s, the wave function is a mathematical tool for predicting measurement outcomes. It is not a description of physical reality as it exists independently of measurement. The collapse of the wave function upon measurement is not a physical process, but simply the updating of our mathematical description when we obtain new information. Questions about what the photon was doing between measurements are, in this view, meaningless. They are not physics questions. They are pseudo-questions arising from our attempt to apply classical concepts to a domain where they don't apply. The Copenhagen interpretation was dominant for decades and remains influential. Its pragmatic approach: if you want to calculate the result of an experiment, do this. Don't worry about what is really happening between measurements, proved enormously productive. The development of quantum electrodynamics, the quantum theory of the electromagnetic force, produced predictions accurate to more decimal places than any other theory in science. The practical toolkit of quantum mechanics powered the development of transistors, lasers, MRI machines, solar cells, and nearly every other technology that defines modern civilization. But the philosophical discomfort never went away. The measurement problem did not dissolve under the weight of practical success. It persisted as a nagging question. If quantum mechanics is a complete description of the physical world, and if quantum mechanics says that systems are in superpositions of states until measured, and if measurement is itself a physical process that ought to be described by quantum mechanics, then when does the superposition end? At what point in the measurement process does the definite outcome emerge? This is the question that Hugh Everett addressed with the many worlds interpretation in 1957. His answer was radical. The superposition never ends. Every measurement simply entangles the measuring apparatus, and eventually the observer, and the rest of the universe with the quantum system. From the perspective of an observer in one branch of the resulting superposition, a definite outcome appears to have occurred. But from a larger perspective, all outcomes are occurring simultaneously in different branches of an ever-expanding quantum multiverse. Many physicists today accept a version of the many worlds interpretation, or find it to be the most logically consistent option available. Others find the proliferation of unobservable parallel universes to be an unacceptable cost. The debate continues. What the delayed choice quantum eraser adds to this debate is a concrete, experimentally testable demonstration that the apparent retroactive definition of the past is a real feature of quantum mechanics, not a theoretical artifact. It is not enough to say that quantum systems are in superpositions before measurement, because the experiment shows that the outcomes of spatially separated measurements are correlated in ways that depend on the sequence of measurements, in a way that looks, from the outside, like backward causation. In the many worlds interpretation, this is explained without backward causation. The correlations simply reflect the fact that all outcomes are occurring, and the experienced history in any given branch is consistent. In retrocausal interpretations, the backward causation is taken seriously as a real feature of the world. In relational interpretations, there is no single objective history to be correlated. Different observers simply have different relational descriptions of the same system. In the Copenhagen interpretation, the question of why the correlations exist the way they do is discouraged in favor of simply calculating that they do. Each of these frameworks leads to a different picture of what the delayed choice quantum eraser is actually showing us. But all of them agree that the experiment is genuine, the results are correct, and the naive classical picture of a photon with a definite history, traveling a definite path through the universe for billions of years before arriving at our telescope, is simply wrong. There is one more dimension to these experiments worth exploring: what they imply about the relationship between information and physical reality. In the delayed choice quantum eraser, the crucial variable is not energy, not momentum, not force. It is information. Whether the signal photon behaves as a wave or a particle depends on whether information about its path is available anywhere in the universe. Not whether anyone checks that information, not whether it is recorded in any accessible location. The mere fact that the information exists or does not exist, in principle, this is what determines the physical behavior of the particle. This is a profound statement. It suggests that information is not just a description of physical reality. It is a constitutive ingredient of physical reality. The physical state of the universe depends on what information exists within it. John Wheeler, later in his career, formulated this idea with his characteristic compressed brilliance as the phrase, "it from bit." The idea that every element of physical reality, every field, every particle, every force, every space-time event, ultimately derives its existence from answers to yes or no questions, bits of information. In this view, the universe is at its foundation, an information processing system, and physical reality emerges from the structure of that information. This idea connects to developments in theoretical physics that emerged at the end of the 20th century and continue to develop today. The holographic principle, emerging from string theory and black hole thermodynamics, suggests that all the information required to describe the physics within a three-dimensional region of space can be encoded on the two-dimensional surface bounding that region. The implication is that three-dimensional physical reality is, in some sense, a projection of two-dimensional information. The connection between quantum information and quantum gravity is one of the most active areas in theoretical physics. Researchers are exploring whether the entanglement structure of quantum systems is what generates the geometry of spacetime, whether the fabric of space and time itself emerges from the web of quantum correlations between particles. In this framework, the strange correlations demonstrated by the quantum eraser are not just curiosities about photon behavior. They are hints about the deep structure from which space, time, and gravity all emerge. We are a long way from having confirmed answers in these directions. But the journey from the double-slit experiment to the delayed choice quantum eraser to the holographic principle to the emergence of space-time from entanglement represents one of the most remarkable intellectual progressions in scientific history. Each step reveals that reality is less like what we thought and more like something we are still learning to think. When scientists first discovered the double-slit result more than a century ago, it seemed like a strange quirk of the quantum world, confined to the very small. As the experiments became more precise and the implications more carefully analyzed, it became clear that the strangeness was not a quirk. It was a fundamental feature of how the universe works. The weirdness did not go away as we looked more carefully. It became more strange. The delayed choice quantum eraser is, in this sense, not the end of a line of inquiry. It is a waypoint on a journey that is still in progress. Every experiment that confirms its predictions raises new questions. Every interpretation that explains its results creates new puzzles. The universe seems to be inexhaustible in its capacity to surprise us. What we take away from these results, more than any specific philosophical conclusion, is a deep lesson about the relationship between observation and reality. The classical picture, a world of definite objects with definite properties, moving through a definite history, indifferent to whether anyone looks, is an approximation that works extraordinarily well at human scales. It works so well that we mistake it for reality itself. The quantum world shows us that this approximation has limits. At the scale of individual particles, the definiteness breaks down. Properties become probabilistic. Histories become superpositions. And the act of observing, of making information available, is not separate from the physical world. It is part of the physical world. It participates in determining what the physical world is. This is not mysticism. This is not a claim that consciousness creates reality in any loose spiritual sense. It is a precise, mathematical, experimentally confirmed statement about how quantum systems behave. The information-theoretic character of quantum mechanics is rigorous, not vague. The correlations are measured in numbers, not in feelings. But rigorous and strange are not opposites. The universe is precisely, rigorously, measurably stranger than it looks. The photon that is, right now, on its way to our telescopes from a distant quasar, a photon that left its source before the Earth existed, does not yet have a definite history. Whether it has been traveling as a wave, spreading through both sides of a gravitational lens, or as a particle, following a single definite path, depends on a measurement that has not yet been made. Tonight, an astronomer somewhere might make that measurement, and in doing so, they will write the history of a particle that has been traveling for billions of years, writing it in the present, as if it were a book that has been waiting, unread, for all that time. That is not a metaphor. That is, as best as we can tell, an accurate description of how the universe works. The experiment has been done. The results are in. And the universe, it turns out, is keeping its history open until we ask. Understanding the full weight of what the delayed choice quantum eraser tells us requires stepping back from the experiment itself and thinking carefully about what we mean by the word real. It is a word we use constantly and casually, but under examination, it turns out to be remarkably difficult to define in a way that is both precise and consistent with what physics tells us. When we call something real, we usually mean at least two things. First, that it exists independently of whether anyone is observing it. Second, that it has definite properties that are, in principle, accessible to measurement. The chair you are sitting on is real because it would be there whether or not you looked at it, and because it has a definite mass, a definite color, a definite position in space that you could, in principle, measure. Quantum mechanics appears to deny both of these features at the fundamental level. Quantum systems do not have definite properties independent of measurement. Their properties are the results of interactions, not attributes they possess independently. And whether or not they are being observed, whether or not their states are entangled with any measuring apparatus, affects their physical behavior in measurable ways. This is what the double-slit experiment established. The photon does not have a definite path independent of observation. The path is defined by the interaction with the measuring apparatus. Without the measurement, there is no definite path. There is only a wave of probability. The delayed choice quantum eraser goes further. It establishes that the definition of the path can come after the photon has already completed its journey. The path is not merely undefined until measurement. It is retrospectively defined by a measurement made after the fact. The past behavior of the photon is not fixed before the measurement, but is established by it. From this follows an uncomfortable conclusion. If we trace the history of any physical system backward in time, what we find is not a sequence of definite events, but a superposition of possibilities that were retrospectively collapsed by the measurements made later. The history we attribute to the universe, the story of how it evolved from the Big Bang through stellar formation and planetary formation, and the emergence of life and civilization, and finally to the present moment, is not a story that was being written in real time as events unfolded. It is a story that is being written now, from the present, as we make measurements and establish correlations between present observations and past states. The universe, in this view, is not a completed tapestry that we are examining from one end. It is an ongoing conversation between the present and the past, in which the questions we ask now shape the answers we receive about then. This is a radically different relationship between observer and observed than anything in classical physics. In Newton's mechanics, the observer is irrelevant. The universe obeys deterministic laws that would generate the same future from the same past, regardless of whether any observer existed. In quantum mechanics, the observer, or more precisely, the measuring apparatus, the interaction that extracts information, is constitutively part of the physical description. One of the most remarkable things about quantum mechanics is that this constitutive role of observation does not introduce arbitrariness or unpredictability into physics. The correlations between measurements are precisely predicted by the quantum formalism. The wave function evolves deterministically, according to the Schrödinger equation between measurements. The probabilities of different outcomes are exactly calculable. The no-communication theorem ensures that these correlations cannot be used to transmit information in ways that violate causality at the macroscopic level. The whole system is tightly constrained and precisely predictive. What changes is not the precision of physics, but its interpretation. What the equations describe is not the evolution of an objective reality, but the evolution of a probability distribution over possible measurement outcomes. The universe, at its most fundamental level, accessible to quantum mechanics, is not a collection of objects with definite properties. It is a web of correlations between events. John Bell's theorem, proven in 1964, and experimentally confirmed in a series of experiments, beginning with Elaine Aspect's work in 1982 and culminating in loophole-free Bell tests in 2015, established this rigorously. Any hidden variable theory, any attempt to explain quantum correlations by invoking pre-existing definite properties that measurements simply reveal, either fails to reproduce the predictions of quantum mechanics or requires non-local connections between distant systems. Since quantum mechanics has been confirmed with extraordinary precision, we are forced to accept that either definite pre-existing properties do not exist, or the universe is non-local in some fundamental sense, or both. The delayed choice experiments add a temporal dimension to this conclusion. It is not just that spatially separated measurements are correlated in ways that cannot be explained by shared pre-existing properties. Temporally separated measurements, measurements made at different times, are also correlated in ways that cannot be explained by the earlier event, having a definite state that the later measurement simply reveals. The later measurement participates in defining what the earlier event was. Space and time, in this sense, are treated symmetrically by quantum correlations. Just as quantum entanglement produces non-local correlations across space, quantum mechanics appears to produce what we might call non-temporal correlations across time. The correlations jump across spatial separation and across temporal separation in exactly the ways that quantum mechanics predicts and that no classical account can explain. These results have practical implications that are just beginning to be explored. Quantum cryptography, quantum computing, and quantum communication all exploit the strange properties of quantum systems to achieve capabilities that are impossible with classical physics. Quantum key distribution uses entanglement to guarantee absolutely secure communication. Quantum computers use superposition to explore many computational paths simultaneously. Quantum teleportation uses entanglement to transmit quantum states across arbitrary distances. As these technologies develop, the deep questions about the nature of quantum reality become increasingly relevant not just to physicists, but to engineers, cryptographers, and computer scientists. Understanding what quantum systems actually are, whether they have definite states or not, how measurement affects them, how entanglement works across space and time matters for building reliable and secure quantum technologies. The delayed choice quantum eraser, in this context, is not just a philosophical curiosity. It is a probe of the deepest properties of information in the physical world, properties that will determine what quantum technologies can and cannot do, what limits they face, and what new capabilities they might enable. The experiment sits at the intersection of the practical and the profound. It is a laboratory demonstration that can be performed with laser equipment and optical components costing a few $1,000s. And it is a window into questions about the nature of time, information, and reality that humanity has been grappling with since before recorded history. What makes the result so powerful is precisely this combination. It is not speculation. It is not philosophy. It is a controlled experiment with precise and reproducible results that force us to abandon one of our most fundamental assumptions about the world. The assumption that the past is settled, fixed, and independent of what we do now. In the face of this result, we have two options. We can dismiss it as a mere quantum oddity, confined to the microscopic world of particles, irrelevant to the macroscopic world of our experience. Or we can take it seriously as a statement about the nature of reality at its most fundamental level and ask what it implies for how we understand existence. The history of science suggests that the second approach is more productive. Every time we have taken strange quantum results seriously rather than dismissing them, we have learned something profound. The quantization of energy led to modern electronics. The uncertainty principle led to the understanding of atomic stability. Quantum tunneling led to nuclear fusion in stars and to the tunneling microscope. Quantum entanglement led to quantum cryptography. In each case, the strangeness of the quantum world turned out to encode real and important information about how reality works. The delayed choice quantum eraser is, in this tradition, an invitation. It is an invitation to revise our concept of time, to reconsider what we mean by a past event, to question the assumption that the universe has a definite history that exists independently of our observations. Some physicists respond to this invitation by developing new theoretical frameworks, retrocausal theories, relational interpretations, quantum gravity approaches that treat time as emergent. Others respond by pushing the experiments further, testing the limits of delayed choice effects at greater distances with more complex systems under more extreme conditions. Still others respond by exploring the technological implications of quantum correlations across time. All of these responses take the experiment seriously. They all accept that quantum mechanics is telling us something real and important about the structure of reality. They differ in what they think that something is. What we can say with confidence is this: the universe is not the fixed, deterministic, objective machine that classical physics described. It is not a completed history waiting to be discovered. It is a process of becoming a continuously unfolding interaction between systems that creates definite events from an underlying substrate of possibility. In this process, the act of measurement is not a passive observation of something that would have existed regardless. It is an active participation in the creation of the definite from the indefinite. Every measurement we make, every observation we record, every experiment we perform participates in writing the history of the systems we observe. And sometimes, as the delayed choice quantum eraser shows that history reaches back further than we might expect. The photon that arrives at our detector tonight has been traveling since before the Earth formed. Its arrival at our instrument is not the revelation of a pre-existing fact. It is the creation of a fact. A fact that, once created, retrospectively determines what that photon has been doing for billions of years. This is quantum mechanics. Not a metaphor for it, not a loose analogy. This is what the equations predict and what the experiments confirm. Decades of research have not resolved the philosophical questions this raises. They have only sharpened them. And as experimental capabilities continue to improve, as quantum technologies mature, as space-based quantum experiments become feasible, as our ability to maintain quantum coherence in larger and more complex systems grows, the delayed choice quantum eraser and its relatives will continue to be among the most important experiments in the investigation of what the universe actually is. The results do not add up, not if you insist on a classical picture of time, but in the quantum picture that our experiments have forced us to accept, they add up perfectly. The universe is consistent. Its accounting is precise. It is just that the ledger is organized differently than we thought, and the entries in the past are filled in by the measurements we make in the present. The experiment ran. The numbers came in. And time, it turns out, does not work the way any of us expected. Keep watching the sky. The universe has more to tell us. And every time we build a better instrument and ask a sharper question, the answer comes back stranger and more precise. That, ultimately, is what science is. The ongoing process of asking the universe questions it has not yet been asked, and discovering that the answers rearrange everything we thought we knew. The delayed choice quantum eraser is one of the finest examples of that process in action. The question was asked, the answer came back, and physics has never been quite the same since. There is a reason the delayed choice quantum eraser continues to occupy a central place in discussions of quantum foundations long after its initial confirmation. Most physics experiments settle questions. This one generates new ones faster than it closes old ones. Each time researchers refine the setup, each time they push the apparatus harder, each time they close a loophole in the experimental design, the implications grow larger rather than smaller. Consider what it means that this effect has now been confirmed with atoms as well as photons. Photons are massless particles of light traveling at the maximum speed the universe allows. It might be tempting to explain away the delayed choice results for photons by arguing that light is somehow special, that the time-symmetric nature of electromagnetic radiation creates unusual behavior that would not apply to matter. The 2012 Australian experiment with helium atoms rules this out. Helium atoms have mass. They travel at speeds far below the speed of light. They interact with gravity. They are, in every ordinary sense, particles of matter that obey the same rules as everything else. And yet, under delayed choice conditions, their behavior exhibits exactly the same retroactive correlation between present measurement and past behavior that photons show. This means the effect is not about light. It is about quantum mechanics itself. It is a feature of the quantum description of any system, regardless of whether that system is made of massless photons or atoms of ordinary matter. If atoms obey this rule, then so do molecules. And if molecules obey it, then the same logic traced carefully through the physics applies to everything composed of molecules, which is everything we can see and touch. The classical definiteness of the macroscopic world is not a feature of the underlying quantum mechanics. It is something that emerges from quantum mechanics when systems are sufficiently large, sufficiently complex, and sufficiently entangled with their environment. This emergence is described by the process of decoherence. When a quantum system interacts with its environment, with air molecules, with electromagnetic radiation, with the thermal fluctuations of its surroundings, it becomes entangled with the environment. The quantum superposition of the system does not disappear, but it becomes effectively invisible at the level of the system alone. The interference between different states of the system is washed out by the entanglement with the enormously complex environment. For all practical purposes, the system behaves classically. Decoherence is extraordinarily fast for macroscopic objects. A large molecule isolated in vacuum can maintain. Quantum coherence can remain in a genuine superposition of states for measurable times. A grain of sand in ordinary air loses its quantum coherence in an inconceivably small fraction of a second, far shorter than any timescale measurable with current technology. A human being loses quantum coherence, essentially instantaneously. This is why we do not experience quantum superpositions directly. It is not that quantum mechanics stops applying at human scales. It is that decoherence renders the quantum superpositions of large systems undetectable in practice. The interference effects that produce the double-slit pattern for individual photons are averaged out into invisibility for objects we can see. But decoherence does not solve the measurement problem. It explains why large systems look classical. It does not explain what happens to the superposition when measurement occurs, whether it genuinely collapses to a definite state, whether it continues as a superposition that simply branches, or whether something else entirely is going on. Decoherence converts quantum superpositions into apparent classical probabilities, but it does not explain where the definite outcomes come from. And crucially, decoherence does not erase the quantum correlations between systems that have interacted in the past. Entanglement, once established, persists, even as decoherence scrambles the local quantum behavior of each system. The correlations demonstrated by Bell tests and by delayed choice experiments are correlations between measurement results, and these correlations survive decoherence. They can be demonstrated whenever we manage to isolate the relevant system sufficiently to make the quantum correlations measurable. This is why quantum technology is difficult. Building a quantum computer requires maintaining quantum coherence, preventing decoherence for long enough and with enough precision to perform useful computations. This is technically challenging precisely because the environment is constantly trying to entangle itself with the quantum system and wash out the quantum effects. The engineering challenge of quantum computing is, at its heart, the challenge of fighting decoherence. But it is also why quantum technology is powerful. The quantum correlations that decoherence tries to destroy are a resource. They allow quantum computers to explore many computational paths simultaneously. They allow quantum cryptography to create unbreakable encryption. They allow quantum sensors to measure with precision beyond classical limits. The same quantum correlations that produce the delayed choice quantum eraser results the entanglement between signal and idler photons. The correlations across time are the resource that quantum technologies exploit. Understanding the delayed choice results is not just a matter of philosophical interest. It is, increasingly, a matter of engineering. As quantum computers grow in capability, the distinction between what quantum mechanics tells us about the history of a system and what classical physics would say becomes practically important. Quantum error correction, the technique that allows quantum computers to function despite decoherence and other sources of noise, depends on maintaining coherent quantum states. The state of a quantum memory encodes information that has a quantum character. It is not simply a definite value stored and waiting to be retrieved, but a superposition of values that only acquires a definite form when measured. The history of what a quantum memory contains is, in the quantum mechanical sense, not fully defined until it is read. This is the delayed choice principle applied to practical technology. The quantum memory is in a superposition of states until measured, and the act of measurement retrospectively defines what state it was in. Engineers building quantum systems must grapple, practically, and not just philosophically, with the fact that their systems do not have definite states between measurements. The relationship between quantum mechanics and time does not only manifest in laboratory experiments, it is embedded in the mathematical structure of the theory at the deepest level. The Schrödinger equation, which governs how quantum states evolve between measurements, is time-symmetric in a precise mathematical sense. If you replace the time variable in the Schrödinger equation with its negative, you get an equation that is equally valid. The equation does not have a preferred direction of time. This means that quantum mechanics itself does not contain an arrow of time. The quantum state can evolve forward in time or backward in time with equal validity. The sense in which measurements produce definite outcomes, the sense in which the past is settled and the future is open, is not encoded in the Schrödinger equation, but arises from something additional, the measurement postulate, which says that when a measurement is made, the wave function collapses to a definite state. But the measurement postulate is the most philosophically problematic part of quantum mechanics. It is not derived from the Schrödinger equation. It is added by hand, as an additional rule. It does not emerge from a deeper physical principle. It simply asserts, when this kind of interaction happens, this kind of update occurs. The fundamental question of why and how this update occurs, and what exactly counts as a measurement, remains unanswered. Different interpretations of quantum mechanics handle this postulate differently. In Copenhagen, it is simply accepted as a rule without further explanation. In many worlds, it does not exist. There is no collapse, only branching. In retrocausal theories, the update is the result of bidirectional information flow in time. In objective collapse theories, the wave function genuinely collapses through a physical mechanism that is not the Schrödinger equation, perhaps triggered by gravity or by some threshold of complexity or mass. Objective collapse theories are among the few interpretations that make predictions different from standard quantum mechanics. If the wave function collapses through a physical mechanism at a specific threshold, if, say, the gravitational energy associated with two distinct positions of a sufficiently massive object triggers collapse, then experiments testing the quantum behavior of increasingly massive objects should eventually see deviations from standard quantum mechanics. This is one of the frontiers of current experimental research. Groups around the world are attempting to demonstrate quantum superposition in objects of increasing mass, looking for any deviation from quantum predictions that might signal the onset of objective collapse. So far, quantum mechanics has passed every test. The superposition principle has been confirmed for particles containing tens of thousands of atoms. No deviation has been found. If quantum mechanics continues to pass these tests as experiments probe larger and more massive systems, it will increasingly support the view that quantum mechanics is universally valid and that the classical world of definite objects emerges entirely from quantum mechanics through decoherence and entanglement, without any additional physical collapse mechanism. If instead deviations are found at some scale, it will be one of the most important discoveries in the history of physics, the identification of the physical mechanism that produces definite classical reality from quantum superpositions. Either outcome would be extraordinarily informative. Either quantum mechanics extends all the way to macroscopic scales and the classical world is entirely emergent, or quantum mechanics breaks down at some scale and a new, more fundamental theory takes over. The delayed choice quantum eraser, in both scenarios, has played its role. It has established that as long as quantum mechanics holds, the retroactive correlation between present measurement and past behavior is real. It is confirmed that the universe does not have a definite past, independent of present observation within the quantum mechanical regime. Whatever more fundamental theory eventually supersedes quantum mechanics, it will have to account for this result. Physics proceeds this way. Experiments constrain theories. Results that hold up under rigorous testing are not negotiable. Whatever the correct interpretation of quantum mechanics turns out to be, it must reproduce the predictions that experiments like the quantum eraser have confirmed. The results are the fixed points around which theories must be built. And the result of the delayed choice quantum eraser is, stated plainly, the history of a quantum system is not fully determined prior to measurement. The measurement, made in the present, determines what the past was. Time, at its most fundamental level accessible to experiment, does not flow in only one direction. The future participates in determining the past. The present is not downstream of a fixed history. It is in active dialogue, with a history that remains indeterminate until the dialogue occurs. This is what the experiment shows. Not a theory about it, not a speculation, the experiment. And that, for all its strangeness, is the kind of result that makes physics what it is. The systematic and rigorous investigation of a universe that is under no obligation to match our expectations, and that consistently, reliably, and precisely exceeds them in ways we never anticipated. The results don't add up if you expect the universe to be the ordinary, classical, causally straightforward place we experience in everyday life. They add up perfectly if you accept that the universe, at its core, is quantum mechanical, and that quantum mechanics is stranger than anything we invented before we were forced by experiment to accept it. The experiment ran, time was tested, and time failed the test we designed for it. It turned out not to be the simple, forward-flowing arrow we assumed. It turned out to be something more intricate, more interconnected, and far more interesting. That discovery is not the end. It is the beginning of a set of questions we are only now beginning to know how to ask. And every answer we find opens onto another question, deeper and stranger, waiting on the other side. The universe keeps its secrets carefully, but it does not keep them perfectly. And every so often, in a laboratory somewhere, a precisely designed experiment asks the right question at the right moment, and the universe answers, and the answer changes everything. This was one of those moments. The delayed choice quantum eraser was one of those experiments. And what it told us about the nature of time, history, and the relationship between observation and reality will continue to shape physics for as long as physics is practiced. Stay curious. The universe rewards the question. Let us return, one more time, to the moment in the laboratory when the delayed choice quantum eraser is actually running. Not to the philosophical implications, not to the theoretical frameworks, but to the raw physical facts of what is happening in that room. A laser fires. A crystal receives a photon and converts it into two entangled photons. These two photons separate. One heads toward a screen, the other heads toward a maze of beam splitters. The first photon hits the screen and leaves a mark. That mark is recorded. At that instant, the second photon is still traveling through the optical apparatus. It has not yet encountered the beam splitters that will determine whether its path information is preserved or destroyed. Nanoseconds pass. The second photon reaches the beam splitters. Its path information is either preserved or erased, depending on the specific configuration the experimenter set up. The computer collects all the data. Thousands of events are recorded. The experimenter asks the computer to sort the first photon's landing positions based on where the second photon ended up. The sorting is done. The subsets are plotted. And there it is, among the first photons whose twins had their path erased, a clear interference pattern. Bright bands and dark bands, unmistakable, crisp, with the exact spacing predicted by quantum mechanics. Among the first photons whose twins had their path preserved, no interference pattern, two broad clumps, the signature of particle behavior. The first photon hit the screen before the second photon reached the apparatus that determined its path. The outcome of that future measurement is written into the past behavior of the first photon. The correlation is exact. It cannot be explained by any common cause shared by both photons before they separated, because the which path measurement happens after the signal photon has already landed, and the erased path measurement also happens after the signal photon has already landed. Nothing that was true at the moment the photons were created could have produced this pattern. Something that happened after the signal photon landed, the future measurement of the idler is correlated with where the signal photon landed in the past. This is the experimental fact. This is what was measured. This is what every replication of the experiment confirms. There is no sleight of hand here. There is no subtle error in the experimental design. The delayed choice quantum eraser has been analyzed, critiqued, replicated, and extended for more than 2 decades. The result stands. Now consider what this means at a slightly larger scale. Consider not a single photon, but the light from a star. Every night, light from billions of stars arrives at Earth. Some of that light has been traveling for thousands of years. Some of it has been traveling for millions, some for billions. As it travels, it has been, in quantum mechanical terms, in a superposition of states. The moment any of that light interacts with a detector, a telescope, a camera, a photovoltaic cell, a human retina, that interaction constitutes a measurement. The superposition collapses. The history of the photon is defined. What path it traveled from its source to the detector is retrospectively established. None of this is visible to us in everyday experience because decoherence operates at the scale of telescopes and retinas so rapidly that the quantum character of the light is lost before we can observe it. But the underlying quantum process is the same. The arrival of starlight at a detector is, at the quantum mechanical level, a delayed choice measurement. The history of the photon is not fixed until it arrives. Every photon that reaches your eye from a star has been, in this sense, in an indeterminate state since it left that star. Your act of looking at the night sky is, quantum mechanically, participating in writing the history of particles that left their sources, perhaps millions of years ago. The universe you observe is not a pre-existing record that your observation simply reads. It is a history that your observation participates in creating. This does not make your act of looking any less real or any less physical. It makes it more interesting. You are not a passive observer of a predetermined universe. You are a participant in the ongoing process by which the universe's history is written. This is not a comfortable conclusion. It challenges the most basic assumption of how we relate to the world. We think of the world as something that is out there, independent of us, proceeding on its own, regardless of our attention. We think of observation as passive, as discovery, as finding things that were already there. Quantum mechanics suggests that at some level, this picture is wrong, that observation is active, that measurement participates in creating the definite from the indefinite, that the history of the universe is being written continuously in the present. But, and this is crucial, it does not suggest that individual conscious observers are creating reality through acts of will. It does not suggest that the universe is different depending on what individual people believe or want. Quantum mechanics is precise, mathematical, and predictive. The correlations it describes are rigorous and universal. The role of observation is not psychological but physical. It is the role of physical interaction, of information exchange, of entanglement between systems. The quantum eraser does not tell us that the universe is whatever we want it to be. It tells us something much more specific and much more interesting, that the physical world does not consist of definite facts prior to measurement, that measurement participates in creating those facts, and that this creation can, in specific ways, retrospectively determine what the past was. That is a scientific claim. It is supported by experiment. It is constrained by mathematics. And it is genuinely deeply different from the classical picture of reality. The history of physics is a history of such revisions. Galileo revised the Aristotelian picture of motion. Newton unified terrestrial and celestial mechanics under a single set of laws. Maxwell unified electricity, magnetism, and light. Einstein revised our understanding of space, time, and gravity. Quantum mechanics revised our understanding of matter and energy at the smallest scales. Each revision seemed impossible before it was made, obvious in hindsight, and productive of new questions that the previous framework could not even formulate. The classical framework could not ask the questions that quantum mechanics answers. The quantum framework is revealing questions that may require yet another revision, perhaps related to quantum gravity, perhaps related to the emergence of time, perhaps related to something we have not yet conceived. The delayed choice quantum eraser is part of this ongoing story. It is not the endpoint. It is a data point, a confirmed result, a constraint on any future theory that claims to describe the physical world. Any theory that correctly describes the physical world must reproduce this result. And any theory that reproduces this result must accommodate, in some way, the fact that the past is not fully settled until measurements are made in the present. Whatever comes next in physics, it will have to reckon with this. The experiment has been done. The correlations are measured. The history of quantum systems is not fixed until we look. And the universe, patient and indifferent and astonishingly strange, continues to wait for our next question. The greatest scientific discoveries are not the ones that close doors. They are the ones that open them. The delayed choice quantum eraser opened a door that physicists are still walking through, still exploring, still following into territory that none of the founders of quantum mechanics could fully have anticipated when they began untangling the quantum nature of light more than a century ago. The experiment ran. The results don't add up by the old rules. By the new rules that the universe has shown us, through careful and rigorous experiment, that it actually follows. The results are exactly what they should be. Time is not what we thought, and that is the beginning, not the end, of understanding what it is. There is one more layer to this story that deserves careful attention, and it concerns not just what the experiment shows, but how it fits into the broader map of quantum weirdness that physicists have been charting for the better part of a century. The delayed choice quantum eraser belongs to a family of experiments that test quantum non-locality, the phenomenon whereby measurements on quantum systems produce correlations that cannot be explained by any classical account, involving locally acting influences. The most famous members of this family are the Bell test experiments, which test correlations between spatially separated measurements. The quantum eraser tests correlations between temporally separated measurements. Together, they paint a picture of a universe in which quantum correlations are non-local in both space and time. This temporal non-locality is less widely discussed than spatial non-locality, but it is equally well established and arguably even more counterintuitive. We have some intuitive experience of spatial non-locality, or at least we can construct analogies for it. We can imagine, however imperfectly, two distant objects being correlated because they were in contact in the past and exchanged information that determined their future behavior. We know this is not the correct explanation for quantum entanglement. The Bell tests rule it out, but the intuition is at least conceivable. Temporal non-locality has no comparable intuitive foothold. The idea that a measurement made now determines what happened before, that the present defines the past rather than the other way around, has no classical analog. There is nothing in everyday experience that prepares us for it. It requires a genuine revision in our conceptual picture of time and causality, not just an extension of familiar ideas. And yet this is what the experiment shows. The Idler photon's measurement in the present determines the signal photon's behavior in the past. Not because information traveled backward in time, the no-communication theorem prevents that from being exploitable, but because the quantum state of the entangled pair is genuinely indeterminate prior to measurement, and the measurements at different times are correlated in ways that cannot be reproduced by any theory that assigns definite properties to the photons before measurement. This conclusion follows from the experimental results by essentially the same logic that Bell tests use to rule out local hidden variables in the spatial case. If the signal photon had a definite history, a definite answer to whether it behaved as a wave or a particle from the moment it was created, then its correlation with the future Idler measurement would have to be explained by this pre-existing definite history. But the correlations cannot be reproduced by any such hidden variable theory. They require that the past behavior of the signal was genuinely indeterminate until the future measurement of the Idler determined it. This is a theorem, not just an experimental observation. The experimental results rule out, by the same logic as Bell's theorem, any theory in which the signal photon has a definite history from the moment of creation. The past is not just unknown, it is undefined. The implications of this for our concept of history extend far beyond quantum optics. If the fundamental constituents of matter, the photons, electrons, quarks, and other quantum fields that make up everything, do not have definite histories until those histories are established by measurement, then what is the status of the history of the universe? The universe began, as best we can determine, approximately 13.8 billion years ago in an extremely hot, dense state that we call the Big Bang. Since then, it has expanded and cooled, forming hydrogen and helium in the first few minutes, then stars and galaxies over hundreds of millions of years, then heavier elements in stellar furnaces and supernovae, then planets, and eventually, life. This is the history of the universe, as we reconstruct it from current observations. But if quantum mechanics applies universally, if the matter and energy that formed stars and galaxies and planets was, before any measurement established its definite state, in quantum superpositions, then the history we reconstruct from current observations is not a history that existed independently prior to those observations. It is a history that our current measurements are retroactively defining. We look at the cosmic microwave background radiation, the afterglow of the Big Bang, now cooled to just a few degrees above absolute zero, visible in all directions of the sky, and we see tiny fluctuations in temperature. These fluctuations are the seeds of all the structure in the universe, the gravitational concentrations that grew into galaxies and galaxy clusters. Our measurements of these fluctuations are, at the quantum mechanical level, measurements that retroactively define the quantum state of the early universe. The history of the universe, in this profound sense, is being written by the measurements we make today. Not in any magical or consciousness-dependent sense, but in the precise, technical sense that quantum mechanics specifies. The quantum state of the early universe was not definite until interactions established it, and the chain of interactions leading to our current measurements is what has retrospectively defined the specific history we observe. This is not yet a fully worked-out theory. The application of quantum mechanics to the entire universe, quantum cosmology, is an active and challenging area of research. The standard tools of quantum mechanics assume a measuring apparatus outside the quantum system, but if the universe is the quantum system, there is no external measuring apparatus. New conceptual frameworks are needed. Several exist. The no-boundary proposal of Stephen Hawking and James Hartle treats the quantum state of the universe as a sum over all possible space-time geometries, with no specific beginning or boundary. The many-worlds interpretation applied to cosmology gives each branch of the universal wave function an equally real history. Consistent histories approaches developed by Robert Griffiths, Murray Gell-Mann, and James Hartle provide a framework for assigning probabilities to coarse-grained histories of the universe in a way that avoids the need for an external observer. None of these approaches has achieved consensus. The question of what quantum mechanics means for the history of the universe as a whole is genuinely open. But the delayed choice quantum eraser, along with the Bell tests and other foundational quantum experiments, constrains what any successful answer must look like. It must accommodate the fact that the history of quantum systems is not fixed prior to measurement. It must accommodate temporal non-locality. It must account for why the macroscopic world appears classical despite being made of quantum constituents. These are the constraints. The framework that satisfies them, while also providing a coherent account of time, history, and reality at the cosmological scale, is still being built. In the meantime, the experiment stands. The result is clear. The photon does not have a definite past until we ask. And asking, in physics, means measuring. Every time a photon from a distant star crosses a telescope mirror and produces a signal in a detector, that act of measurement is writing the history of that photon. The star might have been burning for billions of years, but the photon's specific journey, its exact path through the cosmos, the quantum state it carried across all that distance, was not fully defined until the moment it interacted with the telescope. We are, collectively as a civilization, one of the most complex measurement systems the universe has produced. Our telescopes, our detectors, our scientific instruments of every kind are constantly making measurements that, in the quantum mechanical sense, retrospectively define the history of the systems they observe. The universe that we are in the process of mapping, understanding, and describing is not a universe that existed in full definite detail before we began the mapping. It is a universe whose definite history is being established, in the quantum mechanical sense, through the very process of investigation. That is an astonishing thing to say. It is also, as carefully as we can determine, true. The delayed choice quantum eraser showed it to us. In a laboratory, with a laser and a crystal, and a few beam splitters, physicists demonstrated that a choice made in the present can determine what happened in the past within the constraints set by quantum mechanics and the no-communication theorem, but genuinely and demonstrably, without any classical explanation. The universe is not finished. History is not written. The past is not sealed. It is a conversation, still ongoing, between everything that has ever interacted with everything else across space and, as we now know, across time. And we are part of that conversation. If this conversation with the universe has left you thinking differently about what it means for something to be real, for an event to have happened, for the past to be settled, then the experiment has done its job, not just as a scientific measurement, but as a window into the kind of place we actually inhabit. We built science to understand the world. The world turned out to be stranger than the tools we started with could handle. So we built stranger tools. Quantum mechanics is one of those tools. It is strange in exactly the right ways to describe what we observe. And what we observe, in the delayed choice quantum eraser, and in the decades of quantum experiments surrounding it, is a universe that does not fix its history until it is forced to. The question is not whether this is true. The question is what we do with the knowledge that it is. That question belongs not just to physicists, but to anyone who thinks carefully about what it means to be here. looking outward at a universe that is looking back, and finding, in the looking, what it is.